Please subscribe to support the channel. In the depths of the cosmos, in the hearts of stars, and in the most sophisticated laboratories on Earth, something extraordinary happens that defies our everyday intuition about the nature of reality. Light, that intangible phenomenon we perceive streaming through windows and illuminating our world, can transform into solid matter, into particles with mass that can be touched, measured, and manipulated. Even more remarkably, this process works in reverse. Matter can dissolve entirely, vanishing into pure radiant energy. This bidirectional transformation represents one of the most profound and counterintuitive discoveries of 20th century physics, a revelation that fundamentally challenges everything our senses tell us about the distinction between substance and energy, between the tangible and the ethereal. For millennia, human beings operated under what seemed like common sense. Matter was matter, and light was light. Objects had substance, weight, and permanence. Light was something else entirely, a mysterious emanation that allowed us to see, but which had no mass, no solidity, no existence as a thing unto itself. The philosophers of ancient Greece debated whether light was a substance flowing from objects or from our eyes, but none imagined that light and matter could be different manifestations of the same underlying reality. Even as physics matured through the scientific revolution, these categories remained distinct. Newton's mechanics described how objects moved. His optics described how light behaved. They were separate domains governed by separate principles. The notion that one could become the other would have seemed not merely wrong but nonsensical, like asking how blue could transform into heavy or how Wednesday could turn into iron. Yet in the early years of the 20th century, a young patent clerk in Switzerland developed an idea that would shatter this ancient dichotomy forever. Albert Einstein, working on the theoretical foundations of physics during his spare time, arrived at an equation so simple in appearance, yet so revolutionary in implication, that it would transform our understanding of the universe. That equation, known to nearly everyone even if its meaning remains elusive, consists of just three symbols: E equals mc squared. 5 characters that rewrote the rules of reality. To understand why this equation matters so profoundly to our question of how light becomes matter, we need to unpack what these symbols actually mean. The E stands for energy, that fundamental quantity in physics that represents the capacity to do work, to cause change, to make things happen. Energy comes in many forms in our everyday experience: the kinetic energy of a thrown baseball, the chemical energy stored in gasoline, the thermal energy that makes objects hot, the electrical energy that powers our devices. Before Einstein, these were understood as properties that matter could possess, but they were not thought to be equivalent to matter itself. The M represents mass, the measure of how much matter an object contains. Mass is what gives objects their resistance to being pushed or pulled, their inertia. It's why a bowling ball is harder to accelerate than a tennis ball, why a loaded truck requires more force to move than an empty one. In the classical physics that dominated before Einstein, mass was a conserved quantity. Matter could neither be created nor destroyed, only rearranged. The total amount of mass in any closed system remained constant, an immutable feature of physical law. The C represents the speed of light in vacuum, approximately 300 million meters per second, or about 186,000 miles per second. This is the ultimate speed limit of the universe, the fastest that any influence or information can travel through space. The fact that this particular constant appears in the equation relating mass and energy is already remarkable, but even more significant is that it appears squared, multiplied by itself. Since the speed of light is such an enormous number, squaring it produces a truly staggering value: 90 quadrillion meters squared per second squared, or approximately 9 followed by 16 zeros. When Einstein's equation tells us that energy equals mass times the speed of light squared, it is making a statement far more profound than a simple mathematical relationship. It is asserting that mass and energy are not merely related, but fundamentally equivalent, that they are two faces of the same underlying reality. Mass is a form of energy, an incredibly concentrated form frozen or crystallized in a way that gives it permanence and solidity. The enormous factor of c squared tells us that even a tiny amount of mass represents a colossal quantity of energy. A single gram of matter, about the mass of a paperclip, contains roughly 90 trillion joules of energy, equivalent to the energy released by the atomic bomb that destroyed Hiroshima. Every atom in your body, every particle of matter in the universe, is essentially a vast reservoir of frozen energy. This equivalence immediately suggests something extraordinary. If mass is just a form of energy, then perhaps energy can transform into matter. Perhaps light, which we know carries energy, can somehow congeal into matter. Perhaps matter can dissolve back into pure radiant energy. Einstein's equation doesn't just permit these transformations, it quantifies them precisely, telling us exactly how much energy corresponds to any given amount of mass. The equation is a cosmic exchange rate, a conversion factor between two currencies that we had mistakenly believed to be fundamentally different denominations. But to understand how this conversion actually occurs, we need to examine light itself more closely. What exactly is this phenomenon that can seemingly transform into solid matter? Light, in the modern understanding of physics, is electromagnetic radiation, a self-propagating wave of oscillating electric and magnetic fields that travels through space at the universe's speed limit. In some circumstances, light behaves as a continuous wave, exhibiting properties like interference and diffraction that are characteristic of wave phenomena. Yet in other circumstances, light reveals itself to be composed of discrete packets of energy called photons, particle-like quanta that can be counted individually. This wave-particle duality puzzled physicists for decades and represents one of the fundamental mysteries of quantum mechanics. Light is neither purely wave nor purely particle in the classical sense. It is something for which our everyday language has no adequate analog. A photon is a quantum of electromagnetic energy, a massless particle that nonetheless carries momentum and energy. These particles travel always at the speed of light. They cannot be slowed down or brought to rest, for their very nature depends on motion at this ultimate velocity. The moment a photon is created, whether in the filament of a light bulb, in the nuclear furnace of a star, or in the antenna of a radio transmitter, it springs into existence already traveling at light speed, and it maintains this velocity until it is absorbed by matter or transformed in some interaction. The energy carried by each photon depends on its frequency, the rate at which the electromagnetic field oscillates as the light wave propagates. Higher frequency means more energy per photon. This relationship is expressed in another famous equation, this one formulated by Max Planck in his revolutionary work on blackbody radiation. The energy of a photon equals Planck's constant multiplied by its frequency. Planck's constant is a fundamental quantity that sets the scale of quantum effects, an extremely small number that represents the smallest possible unit of action in the universe. The equation tells us that visible light photons carry relatively modest energies, enough to trigger chemical reactions in our retinas that enable vision, but not enough to do anything dramatic at the level of fundamental particles. However, as we move up the electromagnetic spectrum beyond visible light, photons become progressively more energetic. Ultraviolet photons carry enough energy to damage DNA molecules, which is why excessive sun exposure causes sunburn and increases cancer risk. X-ray photons are more energetic still, capable of penetrating soft tissue while being absorbed by denser bone, which is what makes medical X-ray imaging possible. At the extreme high end of the spectrum lie gamma rays, photons with frequencies so high and wavelengths so short that they carry enormous amounts of energy, enough energy under the right circumstances to do something truly remarkable, to create matter from nothing before. This is where the energy threshold becomes crucial to our story. Not just any photon can create matter from nothing. There are strict requirements imposed by the laws of physics, minimum energy barriers that must be overcome. To create an electron, one of the fundamental particles of matter, you need to supply at least the energy equivalent of its mass. Using Einstein's equation, we can calculate precisely what this is. The mass of an electron multiplied by the speed of light squared yields approximately 8.2 times 10 to the negative 14th joules, or equivalently about 511,000 electron volts, a unit of energy commonly used in particle physics. But creating a single electron by itself would violate fundamental conservation laws, so nature requires that electrons always be created in pairs with their antimatter counterparts, positrons.
Therefore, the minimum energy needed is twice the electron rest mass energy, or approximately 1.022 million electron volts, abbreviated as 1.022 MeV. This is a substantial energy for a single photon, far beyond anything we encounter in everyday experience. The photons of visible light carry energies of only a few electron volts, roughly a million times too feeble to create matter. Even the ultraviolet radiation that causes sunburn operates at energies measured in tens of electron volts. Only gamma rays, produced in radioactive decay, nuclear reactions, and the most violent cosmic events, possess sufficient energy to cross this threshold. This is why we don't observe light spontaneously transforming into matter in our daily lives. The lamps in our homes, the sunlight streaming through the atmosphere, even the most powerful searchlights and lasers generally lack the requisite energy per photon to create particles. The transformation of light into matter requires energies available only in the most extreme environments, the cores of stars, the vicinity of black holes, the exotic conditions of particle physics laboratories, and in cosmic ray interactions high in Earth's atmosphere. When a gamma-ray photon does possess sufficient energy, something remarkable can occur through a process called pair production. The transformation doesn't happen spontaneously in empty space, however. There's a subtle constraint imposed by the conservation of momentum, one of the fundamental principles that govern all physical processes. A photon traveling through empty space carries both energy and momentum, two quantities that must be conserved in any interaction. If a photon were to simply split into an electron and positron in vacuum, it would be impossible to simultaneously conserve both energy and momentum while satisfying the relativistic energy-momentum relationships that govern particle behavior. The mathematics simply doesn't work out. You can't balance the books. Nature provides a solution. The interaction must occur in the presence of a third party that can absorb some momentum without absorbing significant energy. Typically, this role is played by an atomic nucleus. When a high-energy gamma-ray photon passes close to an atomic nucleus, the intense electric field surrounding the nucleus can mediate the transformation. In the most precise language of quantum field theory, the photon interacts with the virtual photons that constitute the electromagnetic field of the nucleus. In this interaction, the gamma-ray photon ceases to exist, and in its place appear two particles, an electron and a positron, particle and antiparticle, matter and antimatter, born simultaneously from pure energy. The electron is one of the fundamental constituents of matter, a member of the family of particles called leptons. It carries negative electric charge and possesses a tiny but definite mass, roughly 9 times 10 to the negative 31st kilograms. Despite being more than 1,800 times less massive than a proton, the electron is substantial enough to be affected by gravity, to have momentum, to possess all the properties we associate with matter. It is categorized as a fermion, meaning it obeys the Pauli exclusion principle that prevents two identical fermions from occupying the same quantum state. This principle is ultimately responsible for the structure of atoms, the diversity of chemical elements, and the solidity of matter itself. The positron, its antimatter twin, is identical to the electron in every respect except one. It carries positive electric charge rather than negative electric charge. It has the same mass, the same spin, the same interaction properties with all forces, except that its electromagnetic interactions are reversed due to its opposite charge. The existence of antimatter was predicted by Paul Dirac in 1928 when he formulated a quantum mechanical equation describing the electron that respected the principles of special relativity. Dirac's equation produced two sets of solutions, one corresponding to electrons with negative charge and another mysterious set corresponding to particles with the same mass but positive charge. Initially, Dirac and other physicists were puzzled by these positive energy solutions, but they eventually realized these solutions described a new form of matter, a mirror image of ordinary particles. The prediction was confirmed in 1932 when Carl Anderson discovered positron tracks in a cloud chamber exposed to cosmic rays. The curved path of the particle in a magnetic field revealed it had the same mass as an electron but opposite charge. Antimatter existed. This discovery validated Dirac's equation and established that for every type of particle, nature provides an antiparticle counterpart. Quarks have antiquarks, protons have antiprotons, neutrons have antineutrons. Even the neutron, which carries no electric charge, has a distinct antiparticle distinguished by having opposite values of other quantum numbers related to quark composition. The requirement that pair production must create both particle and antiparticle together stems from fundamental conservation laws. Electric charge must be conserved, the photon that creates the pair has no charge, so the resulting particles must have charges that sum to zero, hence a negative electron and positive positron. Other quantum numbers like lepton number must also be conserved. The electron has lepton number +1, the positron has lepton number -1, and the photon has lepton number 0. Every conservation law is satisfied when pairs emerge together, maintaining perfect symmetry between creation of matter and antimatter. This symmetry extends to the reverse process, which occurs when matter encounters antimatter. When an electron and positron meet, they can annihilate. They cease to exist as particles, and their entire mass converts back into energy according to Einstein's equation. The mass of both particles, approximately 1.022 MeV divided by c squared, transforms completely into electromagnetic energy. The annihilation typically produces two gamma-ray photons traveling in opposite directions, each carrying roughly 511,000 electron volts of energy. The production of two photons rather than one again satisfies conservation of momentum. Two photons traveling in opposite directions carry zero net momentum, matching the momentum before annihilation if the electron and positron met at low velocities. The energy release in annihilation is total and complete, converting 100% of the mass into energy. This is fundamentally different from chemical reactions like burning, where less than 1/billionth of the mass is converted to energy, or even from nuclear fission, where less than 1% of the mass becomes energy. Antimatter annihilation is the most efficient energy release mechanism possible in our universe. The annihilation of just 1 gram of antimatter with 1 gram of matter would release approximately 180 trillion joules, roughly the energy content of 400,000 tons of TNT, comparable to a large thermonuclear weapon. This makes antimatter simultaneously fascinating for its fundamental physics and concerning for any practical applications, as even microscopic quantities carry destructive potential if not carefully controlled.
Despite its explosive potential, antimatter annihilation occurs naturally and constantly in our vicinity, though in quantities far too small to present any danger. High above our heads in the upper atmosphere, cosmic rays, high-energy particles streaming through space from supernovas, pulsars, active galactic nuclei, and other violent cosmic events, strike atmospheric molecules with tremendous force. These collisions possess enough energy to create showers of particles, including electron-positron pairs generated from the kinetic energy of the collision. A single cosmic ray proton with sufficient energy might create dozens or even hundreds of particle pairs as it plows through the atmosphere, cascading through successive interactions, each generation creating more particles until the energy dissipates. These cosmic ray showers constitute a natural particle accelerator operating continuously in Earth's atmosphere. Primary cosmic rays, predominantly protons traveling at nearly the speed of light, collide with nitrogen and oxygen nuclei in the upper atmosphere. These collisions produce pions and other particles that quickly decay into muons, neutrinos, electrons, positrons, and photons. The positrons created in these processes don't survive long. Within microseconds to milliseconds, they encounter electrons and annihilate, flashing back into gamma rays. Yet before they disappear, some of these antimatter particles reach lower altitudes, and a tiny fraction even make it to sea level. Every second, several cosmic ray particles pass through your body, including occasional positrons. Antimatter is literally touching you right now, albeit briefly before annihilating with the electrons in your tissues. The radiation dose from these cosmic events is tiny, far less than background radiation from natural radioactive isotopes in soil and rocks. Yet cosmic ray showers serve as a reminder that the universe is actively demonstrating matter-energy conversion constantly, performing the ultimate magic trick, creating something from apparent nothingness and erasing it back into light, in a continuous cycle that has persisted since galaxies first formed. Before humans existed, before Earth formed, before the sun ignited, cosmic rays were creating particle-antiparticle pairs and watching them annihilate in the tenuous gases of the early universe. While nature demonstrates these processes on a grand scale, human scientists have learned to recreate and study them under controlled conditions in particle accelerators, the cathedrals of modern physics. These enormous machines use electric fields to accelerate charged particles to velocities approaching the speed of light, then smash them together or into stationary targets. The Large Hadron Collider at CERN, the European Organization for Nuclear Research, straddling the border between France and Switzerland, is the most powerful such machine ever built. It accelerates protons around a circular tunnel 27 kilometers in circumference, bringing them to energies of several trillion electron volts, trillions of times the energy of visible light photons, before colliding them head-on. When two protons collide at these energies, the result is a spectacular demonstration of Einstein's mass-energy equivalence. The kinetic energy of the collision, the energy of motion of particles moving at 99.99999% of light speed, becomes available for creating new particles. In the debris of these collisions, dozens or even hundreds of new particles spray outward: pions, kaons, protons, antiprotons, electrons, positrons, muons, and occasionally more exotic species like bottom quarks, tau leptons, or even Higgs bosons. These particles weren't hidden inside the colliding protons. They're genuinely created from the collision energy, materialized from kinetic energy according to the E=mc² relation. This is matter creation not from light directly, but from kinetic energy. Yet the principle is identical. Energy in one form converts to mass. The accelerator makes visible and measurable a process that our everyday intuition insists should be impossible, making something physical from something that isn't. The particles created in these collisions are completely real, as substantial as the particles that make up the chair you sit on or the device you're reading this on. They have mass, they carry charge, they can ionize atoms as they pass through matter, they leave measurable tracks in detectors. And then, within nanoseconds or microseconds, most of them decay back into other particles or encounter their antimatter partners and annihilate, returning their mass to energy. Particle accelerators are, in essence, factories that manufacture matter from energy, operating at the boundary where the classical distinction between stuff and force dissolves into the quantum realm, where they're recognized as interchangeable. Every particle physics experiment is a demonstration of Einstein's equation in action, a proof that matter is not the permanent, unchangeable substance classical physics imagined, but rather a temporary crystallization of energy that can be melted back into radiation as readily as ice melts into water. To understand why these transformations happen and what they meant for the universe's history, we need to journey back to the beginning, to the first moments after the Big Bang, when the universe itself was a gigantic particle accelerator, far more powerful than anything humans have built or could build. In the earliest fraction of a second after time began, the universe was incomprehensibly hot and dense, filled with energy in the form of an incandescent plasma of particles and radiation. Temperatures exceeded trillions of degrees. Energies exceeded trillions of electron volts, conditions so extreme that matter and antimatter were in constant flux. Every gamma ray had enough energy to create not just electron-positron pairs, but pairs of muons, pairs of pions, even pairs of quarks and antiquarks. Space was filled with a roiling sea of particles constantly being created and destroyed, materializing from photons and annihilating back into photons in a perpetual cycle. Matter and antimatter existed in nearly equal quantities, held in dynamic equilibrium by the ambient temperature. For every particle that annihilated, another pair was created from the surrounding radiation field. The universe was too hot for stable structures to form. Even protons and neutrons couldn't bind together because the ambient energy kept blasting them apart. As the universe expanded, it cooled, and this changed everything. Expansion dilutes energy density and reduces temperatures, like how air cools when released from a compressed container. As temperature fell, photon energies decreased. Eventually, the universe cooled enough that photons no longer possessed sufficient energy to create the heavier particle species. Quark-antiquark production ceased when the temperature dropped below roughly 2 trillion degrees, a tiny fraction of a second after the Big Bang. Muon-anti-muon production stopped around 1/10 of a second after the beginning, when temperatures fell below about 200 billion degrees. Electron-positron pair production finally ceased about 1 second after the Big Bang, when the universe cooled below 10 billion degrees. At each threshold, something crucial occurred. Annihilation continued, but creation stopped. As photon energies fell below the threshold needed to create a particular particle type, any existing particles of that type could still annihilate with their antiparticles, but no new pairs formed. You might expect this would mean that all particles and antiparticles would simply annihilate away, leaving a universe of pure radiation with no matter. Indeed, if matter and antimatter had existed in precisely equal quantities, this is exactly what would have happened. The universe would be filled with photons and nothing else. No atoms, no stars, no planets, no life. Yet obviously, this didn't happen. Matter exists.
abundantly, forming galaxies and stars and planets and people. The fact that you're experiencing these words means that somehow matter survived the annihilation era. This survival represents one of the deepest mysteries in cosmology, the baryon asymmetry, or more generally, the matter-antimatter asymmetry. For reasons not yet fully understood, the early universe contained slightly more matter than antimatter. For every billion antimatter particles, there were 1,000,000,001 matter particles, an asymmetry of about 1 part in a billion, a tiny imbalance that won with cosmic consequences. When the universe cooled below the pair production threshold, that billion-to-1 symmetric component annihilated completely, matter and antimatter destroying each other and filling the universe with radiation. But that one extra matter particle per billion had no antimatter partner to annihilate with. These leftover particles, representing a mere 1 billionth excess, constitute all the matter that exists today. Every atom in every star, planet, and living being comes from this minuscule surplus that survived the Great Annihilation. We are the remnants, the survivors, of a cosmic catastrophe that erased nearly everything, leaving only the tiny asymmetric residue from which structure could eventually form. What caused this asymmetry remains one of the great open questions in physics. The standard model of particle physics, our best current theory of fundamental forces and particles, can generate matter-antimatter asymmetries through mechanisms involving the weak nuclear force and particles called quarks. But the predicted asymmetry is far too small, by factors of billions or more, to account for the observed imbalance. Something beyond the standard model must have operated in the early universe, some mechanism that preferentially produced matter over antimatter, or that caused antimatter to decay slightly faster than matter, or that violated the symmetries between particles and antiparticles in ways we haven't yet discovered. Several theoretical proposals attempt to explain this asymmetry. Leptogenesis suggests that extremely heavy particles in the early universe decayed asymmetrically, producing more leptons than antileptons, and this lepton asymmetry was later converted to a baryon asymmetry through quantum processes. Grand unified theories propose that at sufficiently high energies, all the forces of nature except gravity merge into a single unified force, and the physics of this unification naturally generates matter-antimatter asymmetries. Other theories invoke new physics in the neutrino sector, exotic phase transitions in the early universe, or even the possible role of gravitational effects at the quantum level. Despite decades of theoretical work and experimental searches, the origin of the matter-antimatter asymmetry remains unsolved. A reminder that even our most sophisticated theories leave fundamental questions unanswered. Whatever mechanism created it, this asymmetry meant that when pair production ceased and annihilation concluded, the universe was left with a sea of radiation, the afterglow of annihilation, plus a small residue of matter particles. Those photons from the annihilation epoch still exist today, cooled by the universe's expansion to microwave frequencies, forming the cosmic microwave background radiation that fills all of space at a temperature of about 3 degrees above absolute zero. This relic radiation is literally the light from matter-antimatter annihilation in the first seconds of cosmic history, redshifted and diluted by 14 billion years of expansion, but still detectable by radio antennas as a faint hiss coming from every direction in the sky. The leftover matter particles, mostly protons, neutrons, and electrons, eventually cooled enough to form the first atoms, then the first molecules, then clouds of gas that collapse under gravity to form stars. Inside those stars, nuclear fusion converts matter to energy, a slower and less complete version of the matter-light transformation we've been exploring. The early universe's rapid interconversion between matter and light settled into a more gradual process, but the fundamental principle remained. Matter and energy are interchangeable, and the universe constantly demonstrates this interchangeability through various processes occurring at every scale. To understand these processes at their most fundamental level, we need to adopt the perspective of quantum field theory, the conceptual framework that physicists use to describe reality at the smallest scales. In quantum field theory, the familiar notion of particles as tiny solid objects is replaced by something more abstract and mathematically sophisticated.
Space is filled with fields, mathematical entities that have values at every point in space and time. Each type of particle corresponds to a different field. There's an electron field permeating all of space, a quark field, a photon field, and so forth. Particles themselves are understood as excitations or ripples in these fields, like waves on the surface of a vast ocean. When we say a photon travels from point A to point B, quantum field theory describes this as an excitation in the electromagnetic field propagating through space. The energy and momentum we attribute to the photon are really properties of this field excitation. Similarly, an electron is an excitation in the electron field, a localized ripple carrying the electron's characteristic properties, its mass, charge, spin, and lepton number. In this view, what we call particle creation is really the transfer of energy from one field to another. When a photon converts into an electron-positron pair, the electromagnetic field gives up an excitation, the photon, while the electron field gains two excitations, the electron and positron, one with positive energy and one with negative energy-momentum relationship satisfied by the antiparticle. This field-theoretic perspective explains phenomena that would be mysterious from a purely particle-based viewpoint. It clarifies why particles of the same type are indistinguishable. All electrons are identical because they're all excitations of the same underlying electron field. Just like all water waves are fundamentally the same because they're all disturbances in the same medium. It explains how particles can be created and destroyed. Fields can gain and lose excitations through interactions, just like striking a drum creates vibrations that eventually dampen away. Most profoundly, quantum field theory provides the natural framework for understanding how interactions work. Particles interact by exchanging excitations of force-carrying fields, with photons mediating electromagnetic interactions, gluons carrying the strong nuclear force, and W and Z bosons mediating the weak force. In this framework, even empty space takes on new meaning. What we think of as vacuum, as nothingness, is actually the quantum state where all fields are in their lowest energy configuration. But quantum mechanics forbids fields from being perfectly still. Heisenberg's uncertainty principle requires that field values fluctuate randomly, even in the vacuum state. These fluctuations mean that even in empty space, particle-antiparticle pairs are constantly appearing and disappearing in what physicists call vacuum fluctuations or virtual particle production. A virtual electron-positron pair might materialize for a brief instant, exist for a time so short that direct measurement is impossible, then annihilate back into the vacuum before anyone could detect them. These virtual particles are not merely mathematical artifacts. They have measurable consequences. They affect the energy levels of atoms in subtle ways, producing tiny shifts in spectral lines that have been measured to extraordinary precision. They alter the strength of the electromagnetic force at different distances, causing what's called the running of the coupling constant. They generate the Casimir effect, where two uncharged metal plates placed very close together in vacuum experience an attractive force because the space between them excludes certain wavelengths of virtual photons that can exist in the space outside the plates, creating a pressure imbalance. Virtual particles are as real as anything can be in quantum mechanics, constrained only by their fleeting existence. The creation of virtual particle pairs is restricted by the energy-time form of Heisenberg's uncertainty principle, which states that a quantum system can violate energy conservation by an amount delta E for a time delta t, as long as delta E times delta t is less than or approximately equal to the reduced Planck constant divided by 2. The more energy you borrow from the vacuum to create a virtual particle pair, the shorter the time they can exist before they must annihilate and return the borrowed energy. For electron-positron pairs, which require about 1 mega-electron-volt of borrowed energy, the maximum existence time is around 10 to the negative 21st seconds, a billionth of a second. During this infinitesimal interval, the pair exists as a real disturbance in the quantum fields, but it must disappear before the universe's bookkeeping notices the energy violation. This leads to one of the most exotic predictions in quantum field theory, the Schwinger effect, named after physicist Schwinger, who calculated it in 1951. Schwinger recognized that if you could create an electric field strong enough, you could rip virtual electron-positron pairs apart before they annihilated.
The electric field would push the positron in one direction and the electron in the opposite direction with such force that they'd be separated beyond the distance they could travel in their brief virtual lifetime. Unable to find each other and annihilate, they become real particles, and the energy cost would be extracted from the electric field itself. The required field strength is stupendous, about 10 to the 18th volts per meter, a quintillion volts per meter, or equivalently, the field strength near the nucleus of a very heavy atom, but extended over macroscopic distances. Such fields vastly exceed anything achievable with current technology. The strongest continuous electric fields humans can generate in laboratories are several orders of magnitude too weak. However, some theoretical scenarios might achieve Schwinger limit fields. Near the surface of exotic stars called magnetars, whose magnetic fields produce electric fields when charged particles move through them. In the collisions of heavy ions and particle accelerators, where the combined electric fields of the colliding nuclei briefly spike to extreme values, or possibly in the focus fields of extremely intense laser pulses, an avenue researchers are actively pursuing.
The Schwinger effect represents a fundamental limit on electric field strength. If you tried to create a field stronger than the Schwinger limit, the vacuum itself would break down, spontaneously generating electron-positron pairs that would partially neutralize the field. In this sense, the quantum vacuum acts as a kind of electrical insulator with a breakdown voltage. Push the field too hard, and the vacuum itself ruptures, spilling out matter and antimatter. This is matter creation not from light, not from kinetic energy, but directly from field energy. Electromagnetic fields so intense that their energy density exceeds the threshold to materialize particles from the vacuum structure of space-time itself. A related but distinct phenomenon occurs near the event horizons of black holes in a process called Hawking radiation, predicted by Stephen Hawking in 1974. The prediction emerged from applying quantum field theory in the curved space-time near a black hole's event horizon. Just as virtual particle pairs appear throughout empty space, they appear in the vicinity of the event horizon. Normally, both particles would quickly reunite and annihilate. However, the extreme tidal forces near the horizon, the gradient in gravitational field strength, can pull the pair apart. If one particle falls across the event horizon while its partner escapes, they cannot reunite. The escaping particle becomes real, carrying energy away from the black hole, while the infalling particle has negative energy relative to infinity, reducing the black hole's mass. This is an astonishing conclusion. Black holes are not perfectly black, but instead emit radiation with a thermal spectrum, glowing like hot coals with a temperature inversely proportional to their mass. For stellar mass black holes, this Hawking temperature is fantastically small, far below the temperature of the cosmic microwave background, so such black holes actually absorb more radiation than they emit. But the principle is profound. Given sufficient time, a black hole will evaporate completely through Hawking radiation, converting its entire mass into particles and radiation. A black hole, the most gravitationally bound object possible, will eventually dissolve into light and particles, its tremendous mass transforming entirely into energy radiated away into space. The timescale for stellar mass black holes is incomprehensibly long, many times the current age of the universe. But for tiny primordial black holes that might have formed in the early universe, evaporation could occur within cosmological timescales, producing distinctive gamma-ray signatures that astronomers are searching for. Hawking radiation illustrates how the interplay between quantum mechanics and gravity creates matter from vacuum fluctuations enhanced by space-time curvature. It's a process that connects our theme of light and matter interconversion to the grandest scale phenomenon in astrophysics, suggesting that even the most massive objects ultimately cannot escape the fundamental fluidity between mass and energy that Einstein revealed. While these exotic processes stretch the boundaries of theory, researchers have achieved direct experimental confirmation of photon to matter conversion under controlled conditions.
In the decades following the discovery of pair production, physicists studied the process extensively using gamma rays from radioactive sources and particle accelerators. The Bright-Wheeler process, proposed by Gregory Bright and John Wheeler in 1934, describes the conversion of two photons directly into an electron-positron pair without any nucleus nearby. But this process requires extraordinarily improbable conditions. Two photons must collide head-on with sufficient combined energy, and the probability of such collisions is vanishingly small when using conventional light sources. Recent technological advances in laser technology have made direct photon-photon pair production experimentally accessible. High-intensity lasers can produce photon densities high enough that collisions become probable. In 2014, researchers at Imperial College London proposed an experiment using a two-stage process. First, accelerate electrons to relativistic speeds and slam them into a gold target, producing a beam of high-energy photons. Second, direct this photon beam into a hologram, a tiny gold cylinder, while simultaneously shooting an intense laser beam into the same space. Inside the hologram, the laser creates a thermal radiation field, a dense soup of lower-energy photons. High-energy photons from the first stage collide with photons from the thermal field, occasionally with sufficient combined energy and the right geometry to create electron-positron pairs purely from photon-photon collisions. This experiment, though technically challenging and not yet performed at the time of this writing, represents a holy grail of experimental physics, creating matter from light alone, without borrowing momentum from nuclei or deriving energy from particle kinetic energy. It's the purest realization of Einstein's equation: light in, matter out, following the cosmic conversion rate with mathematical precision. When such experiments succeed, they will demonstrate something that would have seemed like fantasy to scientists just a century ago: that light, shown correctly upon itself, can create substance. While these experiments create matter from light, the universe performs the reverse process continuously and on a colossal scale through nuclear fusion inside stars. Our sun, that familiar ball of light that dominates our daytime sky, is a vast engine of matter-to-light conversion, transforming millions of tons of mass into pure energy every single second. The process occurs through nuclear fusion in the sun's core, where temperatures exceed 15 million degrees Celsius and pressures reach hundreds of billions of times Earth's atmospheric pressure. Under these extreme conditions, hydrogen nuclei, protons, overcome their electromagnetic repulsion and fuse together through a multi-step process called the proton-proton chain, ultimately building helium nuclei from hydrogen. The crucial detail lies in the masses involved. 4 hydrogen nuclei, each with a mass of approximately 1.008 atomic mass units, have a combined mass of about 4.032 atomic mass units. The helium nucleus they form, however, has a mass of only 4.003 atomic mass units. Roughly 0.7% of the initial mass has vanished, not destroyed, but converted into energy according to Einstein's equation. This missing mass, called the mass defect, appears as kinetic energy of the reaction products, energy that eventually works its way outward through the sun as radiation emerging from the surface as the sunlight that illuminates Earth and powers nearly all life on our planet.
The scale of this conversion is staggering. The sun converts approximately 4 million tons of mass into energy every second. 4 million tons, about the mass of 1,000 of the largest container ships afloat, simply ceases to exist as matter every second, transforming instead into the roughly 4 times 10 to the 26 watts of electromagnetic radiation that the sun emits. This has been going on continuously for about 4.6 billion years, and the sun has enough hydrogen fuel to continue for another 5 billion years. Over its main sequence lifetime, the sun will convert about 1/10 of 1% of its total mass from matter into light,
radiating away an amount of mass equivalent to the planet Saturn. Every photon of sunlight that warms your face, every ray that drives photosynthesis in plants, every glimmer of sunshine that brightens our days, represents matter that once existed as hydrogen nuclei in the sun's core, but now exists only as electromagnetic energy. The distinction between matter and light that seems so obvious in our everyday experience dissolves when we recognize that sunlight is literally hydrogen that has been converted from substance to radiation. When you step into sunlight, you are bathing in matter that has ceased being matter, transformed by nuclear fire into pure energy, the stellar implementation of E equals mc squared. All stars perform this alchemy, converting matter to light through fusion reactions appropriate to their masses and compositions. The smallest red dwarf stars fuse hydrogen slowly, burning for trillions of years. Massive blue giants consume their fuel voraciously, converting matter to light at prodigious rates, shining with the luminosity of millions of suns, but exhausting their fuel in just millions of years. The most massive stars proceed beyond hydrogen fusion to fuse helium into carbon, carbon into oxygen, oxygen into neon and magnesium, continuing through silicon until they produce iron. At each stage, a small fraction of mass converts to energy, released as the starlight and neutrinos that carry stellar energy into space. The iron endpoint is crucial. Iron nuclei have the highest binding energy per nucleon of any element, meaning they are the most tightly bound, the most stable configuration of nuclear matter. Fusing iron into heavier elements requires energy input rather than releasing energy. The mass of the products exceeds the mass of the reactants, and the difference must be supplied from outside. Stars cannot generate energy by fusing iron, so when a massive star's core fills with iron, its fusion furnace shuts down. Without the outward pressure from fusion to counteract gravity, the core collapses catastrophically in a supernova explosion, one of the most violent events in the universe. In the extreme conditions of the supernova, temperatures exceeding billions of degrees and densities surpassing that of atomic nuclei, heavy elements beyond iron are forged through rapid neutron capture, and the star's outer layers are blasted into space, seeding the interstellar medium with the chemical elements necessary for planets and life. Supernovae also produce gamma rays with energies far exceeding the pair production threshold. In the intense radiation fields near the explosion, gamma rays create electron-positron pairs copiously, temporarily filling the region with antimatter. The positrons quickly encounter electrons and annihilate, producing additional gamma rays that contribute to the supernova's radiation output. Gamma-ray observations of supernovae have detected the characteristic energy signature of electron-positron annihilation at 511 keV, confirming that these stellar catastrophes briefly generate substantial amounts of antimatter before it annihilates away. The interplay between matter and light in supernovae exemplifies how the universe recycles its substance. Matter in the core fuses, converting some mass to light throughout the star's lifetime. The supernova then partially reverses this, using energy to forge heavier elements. The explosion's gamma rays create matter from light through pair production, which quickly annihilates back to light. The heavy elements dispersed by the explosion eventually incorporate into new stars, planets, and potentially living beings. We exist because of these cycles, because stars spent billions of years converting matter to light and occasionally exploding to forge and distribute the elements heavier than hydrogen and helium. The calcium in your bones, the iron in your blood, the carbon in your DNA, all were synthesized in stellar furnaces and supernova explosions through processes that constantly blurred the line between matter and energy. Understanding matter-energy conversion has moved beyond purely theoretical interest to practical application in several remarkable technologies. Perhaps the most direct medical application appears in positron emission tomography, universally known as PET scanning, a diagnostic imaging technique that literally exploits antimatter annihilation to peer inside living bodies. The procedure begins with radioactive isotopes that emit positrons when they decay, typically fluorine-18, carbon-11, or oxygen-15, incorporated into biologically active molecules like glucose. When injected into a patient, these molecules distribute throughout the body according to metabolic activity. As the radioactive nuclei decay, they emit positrons that travel a few millimeters through tissue before encountering electrons and annihilating. Each annihilation produces 2 gamma-ray photons traveling in opposite directions, each carrying 511 keV, precisely the energy corresponding to an electron's rest mass. An array of detectors surrounding the patient records these photon pairs, and sophisticated computer algorithms reconstruct where the annihilations occurred by finding the points where gamma-ray pairs originated. The result is a 3-dimensional map of where the radioactive tracer concentrated, revealing metabolic activity with exquisite precision. PET scans excel at detecting cancer because malignant tumors typically exhibit elevated metabolic rates, consuming glucose faster than surrounding healthy tissue. The radioactive glucose analog concentrates in tumors, creating bright spots in the PET image that reveal cancer's location even when anatomical imaging shows nothing unusual. Neurologists use PET scans to study brain metabolism, identifying regions with abnormal activity in conditions like Alzheimer's disease, epilepsy, and psychiatric disorders. Cardiologists employ PET to assess heart muscle viability after heart attacks. Every day in hospitals worldwide, medical professionals rely on antimatter annihilation to diagnose disease and guide treatment, a practical application of the matter-light conversion we've been exploring. Nuclear energy, whether from fission reactors or potential future fusion reactors, also relies fundamentally on matter-energy conversion, though less directly than PET scanning. Fission splits heavy nuclei like uranium-235 into lighter fragments, and the combined mass of the fragments is slightly less than the original nucleus. This mass deficit appears as kinetic energy of the fission products and neutrons, energy that heats water to drive turbines and generate electricity. A typical nuclear reactor converts roughly 1 gram of matter into energy per day, an astonishingly small amount that nevertheless generates 1 billion watts of power, enough electricity for a city. The efficiency of this conversion, where milligrams of mass disappear to produce megawatts of power, explains both the tremendous energy density of nuclear fuel and the dangerous intensity of nuclear reactions when uncontrolled. Fusion energy, still under development for practical power generation despite decades of research, promises even greater energy release per unit mass. Fusing deuterium and tritium, heavy isotopes of hydrogen, into helium converts about 0.3% of the mass to energy, roughly 5 times more efficient than uranium fission. If humanity can master controlled fusion, we'll essentially have harnessed the same matter-to-light conversion that powers stars, bringing stellar alchemy to Earth to generate clean, abundant energy from fuel extracted from seawater. The challenge lies in achieving the conditions, temperatures of hundreds of millions of degrees, sufficient density, and adequate confinement time necessary to make fusion self-sustaining and energy positive. Projects like ITER, the International Fusion Experiment under construction in France, aim to demonstrate that controlled fusion power is achievable, potentially revolutionizing civilization's energy infrastructure by turning matter into light in controlled quantities here on Earth.
Even conventional chemical energy has a connection to mass energy equivalents, though the effects are far too small to measure directly. When gasoline burns in your car's engine, chemical bonds break and reform, releasing energy that was stored in the electromagnetic interactions between atoms. This energy release is accompanied by an infinitesimal mass decrease. The combustion products weigh slightly less than the fuel and oxygen that combine to form them. However, the mass change is only about 1/billionth of the total mass, far below any scale's measurement precision. For all practical purposes in chemistry, mass appears conserved, which is why chemists operated for centuries under the assumption that mass couldn't be created or destroyed without noticing any contradiction. Only in nuclear reactions does the mass-energy conversion become large enough to measure, crossing the threshold where Einstein's equation transforms from abstract principle to observable phenomenon. Reflecting on these applications and observations leads us to profound philosophical implications about the nature of reality. For thousands of years, Western philosophy drew a fundamental distinction between substance and accident, between the essential unchanging matter of things and their transient properties and motions. Aristotle categorized reality into 10 categories, with substance, the underlying stuff of which things are made, holding primacy as the foundation upon which properties like quantity, quality, relation, and location rest. Matter was that which persists, that which provides continuity and identity across time. Energy, though not formulated explicitly in ancient thought, occupied the realm of change, motion, potential, things that happen to matter but aren't matter themselves. Einstein's equation collapses this ancient dichotomy. Matter and energy aren't different categories of existence, but different states of the same underlying reality, as interchangeable as ice and water. The electron spinning in an atom, seemingly a tiny permanent chunk of substance, is better understood as a particular energetic configuration, an excitation in a quantum field that could just as well be an energetic photon if circumstances were different. The photon carrying electromagnetic radiation, seemingly an ephemeral disturbance propagating through space, contains the same fundamental essence as solid matter, differing only in how that essence is organized and expressed. This realization undermines the classical notion of permanent substances with essential properties. There are no immutable atoms in the ancient sense, indivisible, unchangeable units of matter. Everything can transform into everything else if sufficient energy is available and conservation laws are satisfied. Particles that appear stable, electrons, protons, and photons, are stable only because no energetically favorable decay paths exist, not because they possess some metaphysical permanence. Even protons, stable on timescales vastly exceeding the universe's age, may eventually decay according to some grand unified theories, dissolving into lighter particles and radiation given enough time. This philosophical implications extend to questions of identity and persistence over time. If you are made of atoms, and atoms are really stable patterns of energy in quantum fields, and those patterns could in principle dissolve into radiation and reform elsewhere, what constitutes your identity? The matter in your body is not permanent. Atoms constantly exchange with the environment through respiration, digestion, and cellular metabolism. Every few years, most atoms in your body have been replaced. Yet you persist as a continuous entity, suggesting that identity lies not in the specific matter that comprises you, but in the pattern, the organization, the information encoded in how that matter is arranged. In this view, you are more like a wave than a rock, a persistent pattern in the flow of matter and energy through space and time. Just as a wave in the ocean persists as a recognizable entity even though the water molecules that comprise it constantly change, you persist as a recognizable person even though the atoms that comprise you constantly exchange with the environment. And just as the wave is ultimately just a pattern of energy propagating through the medium of water, you are ultimately a pattern of energy organizing the extraordinarily complex configuration we call a living human being. The boundary between substance and process, between thing and happening, dissolves when we recognize that things are really processes, patterns maintained temporarily against the universal tendency toward disorder. From a physical standpoint, the interchangeability of matter and energy suggests that the universe is fundamentally a closed system, where the total quantity of mass energy remains constant, even as it transforms between different manifestations. The first law of thermodynamics, energy cannot be created or destroyed, extends to mass once we recognize mass as a form of energy. In every process we've discussed, pair production, annihilation, fusion, fission, even Hawking radiation, the total mass energy before and after remains identical. Particles appear and disappear, matter converts to light and light to matter, but the total sum of energy, including mass energy, stays constant, an immutable feature of physics that reflects deep symmetries in the laws of nature. Yet this conservation occurs against the backdrop of cosmic evolution, where the forms that mass energy takes evolve dramatically over time. The early universe's thermal equilibrium between matter and radiation gave way to a matter-dominated cosmos where most energy exists in the form of particle masses rather than radiation. Stars continue converting matter to light, slowly increasing the ratio of photon energy to matter energy, but the expansion of the universe redshifts photons to lower energies, partially offsetting this effect. The ultimate fate of all structure depends on unanswered questions, whether protons decay, whether dark energy accelerates cosmic expansion indefinitely, whether black holes eventually evaporate through Hawking radiation. If protons are stable and expansion continues, the far future might see all matter locked in black holes or dead remnants. If protons decay and black holes evaporate, the ultimate fate could be a universe of pure radiation, matter having completely converted back to light over timescales of 10 to the 100 years or longer, a reversal of the matter-dominated present, returning to a state resembling the radiation-dominated early universe, but vastly diluted by expansion. These cosmic considerations bring us to the frontiers of current research, where physicists continue pushing the boundaries of understanding matter-light conversion and its implications. One active area involves attempting to create matter directly from laser light, the photon-photon collision experiments discussed earlier. As laser technology advances to produce ever higher intensities and photon densities, the dream of colliding light beams to create particle pairs draws closer to realization. Facilities like the Extreme Light Infrastructure in Europe and the National Ignition Facility in the United States can generate laser pulses with peak powers exceeding petawatts, quadrillions of watts focused into volumes smaller than a grain of sand, producing field strengths and photon densities approaching the Schwinger limit. These ultra-high-intensity lasers might enable observation of quantum electrodynamic effects never before seen in laboratories, including vacuum birefringence, where the quantum vacuum itself behaves like an optical medium that bends light differently depending on polarization. They might achieve the Schwinger effect, ripping electron-positron pairs directly from the vacuum through pure field strength. Such experiments would probe the structure of the vacuum itself, testing whether our theoretical understanding of quantum fields correctly describes nature at the most fundamental level accessible to experiment. Another frontier involves the search for dark matter, the mysterious substance that comprises approximately 85% of matter in the universe, but interacts so weakly with ordinary matter and light that it remains invisible to telescopes. One possibility is that dark matter consists of particles that can convert to ordinary particles or photons under certain conditions, perhaps through rare interactions mediated by new forces unknown to the standard model. Experiments worldwide search for such conversions. Detectors deep underground wait for dark matter particles to occasionally scatter off atomic nuclei or convert into detectable particles. Telescopes scan for gamma rays from dark matter annihilation in the centers of galaxies. Particle colliders attempt to create dark matter particles from high-energy collisions. If dark matter interacts through even extremely feeble coupling to electromagnetic fields, it might occasionally convert to photons, and astronomers could detect these conversion signals as anomalous electromagnetic emissions from regions with high dark matter density. The interface between quantum mechanics and gravity remains another domain where matter-light conversion might reveal new physics. We've discussed Hawking radiation from black holes, but this prediction rests on semi-classical calculations that treat gravity classically while quantizing matter fields. A complete theory of quantum gravity might reveal additional processes where space-time curvature and quantum fields interact in ways we haven't yet imagined. Some quantum gravity theories suggest that space-time itself might be granular at the Planck scale, lengths around 10 to the negative 35 meters where quantum effects of gravity become dominant. At this scale, the distinction between space-time geometry and quantum fields might dissolve entirely, with both emerging from some deeper substrate. Matter and light as we know them might be low-energy approximations of more fundamental entities, and the conversions we've discussed might be shadows of deeper transformations occurring at the Planck scale.
Quantum technologies increasingly exploit vacuum fluctuations and the quantum nature of electromagnetic fields in practical devices. Quantum computers use carefully controlled quantum states of matter, trapped ions, superconducting circuits, photons, and optical cavities to perform computations impossible for classical computers. Quantum sensors achieve measurement precisions approaching fundamental limits set by Heisenberg uncertainty and vacuum fluctuations, enabling detection of gravitational waves, magnetic fields from neural activity, and subtle variations in time and space. Quantum communication systems use entangled photons to establish communication links guaranteed secure by the laws of physics. As these technologies mature, the weird features of quantum mechanics, superposition, entanglement, vacuum fluctuations, wave-particle duality, transition from curiosities studied in physics laboratories to practical tools that enable transformative technologies.
These technological applications underscore how the matter-light interconversion we've explored represents not merely abstract physics, but a fundamental feature of nature with practical consequences. Every photon, every electron, every particle that exists participates in the cosmic dance between matter and energy, a dance choreographed by Einstein's equation and the laws of quantum field theory. The transformations occur across every scale: in the quantum vacuum, where virtual particles flicker in and out of existence; in cosmic ray showers in the atmosphere; in the cores of stars, where matter fuses and converts to light; in the extreme environments near black holes, where vacuum fluctuations become real particles; in the primordial fireball of the Big Bang, where matter and antimatter crystallize from pure energy; and potentially in some distant future, when protons might decay and black holes evaporate, returning all matter to radiation. The narrative we've traced reveals a universe far more dynamic and interconnected than our everyday experience suggests. What appears solid and permanent, the ground beneath your feet, the device in your hand, your own body, is really an elaborate dance of quantum fields in temporary configurations that happen to be stable under current conditions. Those configurations could, under different circumstances, dissolve into radiation and reform as different particles entirely. The light streaming from the sun was once matter in the form of hydrogen nuclei. The matter in your body contains atoms forged in stellar furnaces from energy released in fusion reactions. You are literally made of stardust, but more profoundly, you are made of starlight, of energy that briefly wore the guise of matter in a star's core before dispersing to seed the molecular clouds that formed our solar system. This continuous transformation between matter and light represents one of the deepest insights physics has achieved: that beneath the apparent diversity of phenomena, particles and waves, matter and force, substance and radiation, lies a unified reality where these distinctions are human categories imposed on something more fundamental. Quantum field theory describes this unified reality mathematically, showing how particles and forces both emerge as excitations of quantum fields, how mass and energy are interchangeable manifestations of field energy, how the universe operates according to symmetries and conservation laws that constrain transformations while allowing the constant flux we observe. Einstein glimpsed this unity when he formulated his equation relating mass and energy, though even he might have been surprised by how thoroughly the distinction would blur in subsequent theories. The equation E equals mc squared is simultaneously one of the simplest and most profound statements in all of science. It contains just 3 variables and 1 operation, yet it encapsulates a truth that transforms our understanding of existence: that matter is frozen energy, that light can become substance, that the universe constantly performs transmutations that would have seemed like magic to scientists just a century earlier. Every time astronomers observe a supernova, every time a PET scanner images a patient's metabolism, every time a particle accelerator smashes protons together and creates new particles from kinetic energy, every time cosmic rays strike the atmosphere and spawn particle showers, we witness this fundamental truth in action. The universe is engaged in an eternal recycling process, converting matter to energy and energy to matter, following conservation laws that ensure the total quantity remains constant even as the forms continuously change. What elevates this from mere physics to something approaching poetry is recognizing that we ourselves are products and participants in this transformation. The atoms in your body were forged in stellar nuclear furnaces where matter converted to light. They were dispersed in supernova explosions and incorporated into the molecular cloud that formed the sun and planets. They cycled through Earth's biosphere, passing through countless organisms before temporarily becoming part of you. Eventually, they'll return to the environment and continue their journey through the material cycle. But at an even deeper level, those atoms are temporary configurations of quantum fields, stable patterns in the universal flux of energy that could, under different conditions, dissolve into radiation and cease to exist as matter entirely. This perspective can be simultaneously humbling and exalting. Humbling because it reveals our impermanence at the most fundamental level.
We are ephemeral patterns in a vast sea of transforming energy, no more permanent than waves on an ocean. Exalting because it connects us to the deepest workings of the cosmos. The same physical principles that govern the first instance of creation, the lives and deaths of stars, and the ultimate fate of the universe also govern every atom in our bodies, every chemical reaction in our cells, every thought in our minds. We are not separate from the cosmos observing it from the outside. We are the cosmos observing itself, matter that has temporarily organized into configurations complex enough to ponder its own nature. The mystery that opened our exploration, how can light become matter and matter become light, has an answer now, though the answer itself contains mysteries. Light becomes matter through pair production, when gamma rays create particle-antiparticle pairs, through the Schwinger effect, when electric fields rip particles from the vacuum, through Hawking radiation, when black hole gravity amplifies quantum fluctuations. Matter becomes light through annihilation when particles meet antiparticles, through nuclear fusion when mass deficits convert to energy, through any process where mass decreases and energy radiates away. The conversion follows Einstein's equation with mathematical precision, governed by quantum field theory and constrained by conservation laws, occurring constantly throughout the universe at every scale from the subatomic to the cosmic. Yet within this answer lies deeper mystery. Why does the universe allow these transformations at all? Why should reality be organized such that matter and energy are interchangeable? Why do quantum fields exist, and why do they take the particular forms they do? Electron fields, quark fields, photon fields with specific properties. Why are the fundamental constants, the speed of light, Planck's constant, the electron mass, set to the values they have? Why did the early universe contain slightly more matter than antimatter, allowing structure to form rather than annihilating completely into radiation? These questions push beyond current physics into territory where speculation mingles with hope for future theories. Perhaps string theory or loop quantum gravity or some yet undiscovered framework will someday explain why the universe has the properties it does, revealing that the constants and particles we observe are the only mathematically consistent possibility, or are one solution among a vast landscape of possibilities realized in a multiverse. Perhaps the questions themselves are misguided, reflecting our cognitive limitations in trying to understand a reality that transcends human intuition developed for navigating medium-sized objects at moderate speeds on Earth's surface. What we can say with confidence is that the interconversion of matter and light is not merely possible, but fundamental. Not a rare exotic phenomena, but a ubiquitous process woven into the fabric of reality. It occurs in hospitals where antimatter reveals cancer, in stars where hydrogen becomes sunlight, in the upper atmosphere where cosmic rays create particle showers, in the vacuum where virtual particles briefly materialize, and in the history of the cosmos where matter crystallized from the Big Bang's radiation and will perhaps eventually dissolve back into light in a far future when the last black holes evaporate. This continuous cosmic transformation represents the universe's deepest magic trick, the ultimate transmutation that alchemists sought but found in entirely the wrong place. They thought matter could transform into other forms of matter, lead into gold. The truth is far stranger and more profound. Matter transforms into non-matter, into pure energy, into light itself. And light, under the right conditions, crystallizes back into matter, creating substance from radiation. The transformation is not metaphorical or approximate, but exact and total, following the cosmic exchange rate E equals mc squared, with precision that never errs, governed by laws that have operated unchanged since time began and will continue operating unchanged until time ends, if it ever does. As you contemplate these ideas, photons are striking your retinas, triggering chemical reactions that send electrical signals to your brain, enabling you to process these words. Those photons were created by LEDs or reflected from paper printed with ink, ordinary light with ordinary energies. Yet they share the same fundamental nature as the gamma rays that create matter in particle accelerators and cosmic ray collisions. The difference is only a matter of energy. Scale the frequency up by a factor of 1,000,000,000, and your reading light would spontaneously generate electron-positron pairs from its own photons. The universe maintains no absolute boundary between the light you use to see and the light that can become matter. There is only a smooth spectrum of electromagnetic radiation, and we happen to use the lower energy portion for vision while the higher energy portion performs alchemy. This continuity reminds us that the exotic physics we've explored, pair production, annihilation, the Schwinger effect, Hawking radiation, are not disconnected from everyday experience, but are extensions of the same principles that govern familiar phenomena, revealed by pushing to extreme energies, densities, and field strengths. The universe is consistent, operating according to unified principles across all scales and conditions. Light is always light, matter is always matter, yet they are always interconvertible because they are always, at the deepest level, manifestations of the same underlying reality. Perhaps the most important insight is that reality is far stranger, far more fluid, far more unified than our intuition suggests. The comfortable categories we use to navigate the world, this is a thing, that is energy, matter is solid and permanent, light is intangible and fleeting, dissolve under scrutiny into quantum fields and relativistic equations that describe a universe in constant flux, where nothing is permanent and everything transforms. Accepting this strangeness, integrating it into our worldview, even as it contradicts everyday experience, represents part of the intellectual journey science requires. We must hold simultaneously in mind the practical solidity of matter in our immediate environment and the fundamental fluidity revealed by physics, recognizing both as true in their appropriate contexts. The story of how light becomes matter and matter becomes light is ultimately a story about the nature of reality itself, about how the universe is constructed at its foundations, about the deep principles that govern existence. It is a story that began with Einstein's insight, developed through decades of theoretical and experimental physics, and continues today as researchers probe ever deeper into the quantum realm and cosmic evolution. It is a story with practical applications in medicine and energy and technology, but it is also a story with profound implications for how we understand ourselves and our place in the cosmos. As we look to the future, this story will continue unfolding. New experiments will probe vacuum fluctuations and quantum field theory predictions with unprecedented precision. More powerful lasers will approach the Schwinger limit and perhaps create matter directly from light collisions. Better understanding of the early universe might reveal why matter defeated antimatter. Quantum technologies will exploit the matter-light relationship in ways we haven't yet imagined. And perhaps, if we're fortunate, fundamental breakthroughs in physics will reveal even deeper principles underlying the interchangeability of matter and energy, principles that might unify quantum mechanics and gravity or explain why the universe has the properties it does. Throughout all these developments, one truth will remain. Light can become matter, matter can become light, and this continuous cosmic transformation is fundamental to everything that exists. Every atom in every star, planet, and living being, every photon streaming through space, every particle and every accelerator experiment, every cosmic ray striking the atmosphere, all participate in this eternal dance between energy and mass, between radiation and substance, between the ethereal and the material. The dance follows choreography written into the mathematical structure of the universe itself, equations that describe with perfect precision how much energy corresponds to how much mass, under what conditions transformations occur, what must be conserved, and what may change. We are privileged to live in an era when humanity has uncovered these truths, when we can articulate with mathematical precision something that would have seemed like fantasy to our ancestors, that matter and light are not merely related, but interchangeable, that Einstein's simple equation, E equals mc squared, expresses a cosmic truth as fundamental as any we've discovered, that the universe is unified at a level deeper than superficial appearances suggest,
that knowledge enriches our understanding of existence, transforms our technological capabilities, and reminds us that reality exceeds imagination, that the cosmos is stranger and more wonderful than our everyday experience hints, operating according to principles that challenged our intuitions and expanded our intellectual horizons in ways that continue resonating through science and culture. The light streaming from stars, the matter comprising planets, the radiation filling empty space, the particles composing our bodies, all are threads in the same cosmic tapestry, woven together by the fundamental equivalence of mass and energy, constantly transforming from one form to another while conserving the total amount of existence. This is not metaphor but physical fact, demonstrated in laboratories, observed in telescopes, calculated in equations, and confirmed by every piece of evidence we've gathered about how the universe operates. Light becomes matter, matter becomes light, and in this continuous transformation lies one of the deepest truths we've learned about the nature of reality itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.